I once again welcome all to the session on Raman effect, which is the part of physics syllabus in BSc 5th Sem Paper 2 as prescribed by Karnataka University Dharwad. Today, in this session, I am dealing with experimental study of Raman effect. Here, we will be dealing with the construction, working and observations made in Raman effect. We know that C.V. Raman in 1928 discovered the phenomenon of inelastic scattering, which we call Raman effect. Raman observed that when a beam of monochromatic light is passed through organic liquid like benzene, the scattered light contained other frequencies in addition to that of incident light. The apparatus used by Raman to photograph the Raman shift in several liquids is as shown in the figure. The apparatus was further modified by R.W. Wood. The apparatus consists of a cylindrical glass tube AB of length 10 to 25 cm and cross-sectional area diameter 1 to 2 cm. It is filled with pure, dust-free scattering liquid like benzene. One end of the tube H is drawn into horn shape and blackened from outside to provide a contrasting background for photographic camera. W is an optically plane glass plate used to close the other end of the tube. The glass tube is surrounded by the water jacket J, through which cold water is circulated in order to prevent the overheating of experimental liquid. S is the mercury arc source. F is the filter which permits highly monochromatic light to pass through and fall on the experimental liquid. The intensity of illumination is enhanced by using the semi-cylindrical aluminium reflector R. L is the convex lens used in front of the window which focuses and directs the scattered radiation upon the slit of the spectrograph. The spectrograph must have a large light gathering power and the prism must have the large resolving power. A short focus camera is used to photograph the spectrum. Let us study how the working takes place. So light from the mercury arc source, after suitably filtering, that is a highly monochromatic beam of wavelength 4358 angstrom, is obtained and directed onto the tube. The scattered radiation emerging in the transverse direction through the window W is condensed on the slit of the spectrograph. The spectrograph must have a large light gathering power and the prism must have the large resolving power. A short focus camera is used to photograph the spectrum. On developing the photographic plate, it exhibits a number of Stokes lines, a few anti-Stokes lines, and a strong unmodified line. Let us discuss the observations made in Raman experiment in detail. The simplified energy diagram in the figure illustrates the following concepts. Raman lines are symmetrically placed frequencies on both the sides of the incident light frequency. Stokes lines occur on the longer wavelength side of the original frequency. The longer wavelength side is the lower energy side. Anti-Stokes lines occur on the shorter wavelength or higher energy side of the original line. Stokes lines are always more intense than the anti-Stokes lines. Intensity of anti-Stokes lines is found to increase with the increase in the temperature, while that of the Stokes lines remains unchanged. That is why in the apparatus we use the water jacket to keep the temperature of the scattering material constant. The frequency difference between the modified and the parent spectral line represents the frequency of the corresponding infrared absorption line. Raman lines are found to be strongly polarized. If nu0 is the frequency of the incident light and nu-s is that of the scattered light, then the Raman shift delta nu is given by delta nu is equivalent to nu0 minus nu-s. Raman shift delta nu is independent of frequency of incident light. Raman shift delta nu is the characteristic of scattering substance. For Stokes lines, delta nu is positive, and for anti-Stokes lines, delta nu is negative. Thank you for watching.